Lesson 10.5, Mathematical Induction. Mathematical induction is proofs for some formulas and other types of mathematical proofs. And the basic idea is we're going to show it works when n is 1. And then we're going to show it works for n plus 1. So if it works for the first one and it always works for n plus 1, that must mean it works for the second one. And then the third one, and then the fourth one, and then the fifth one, and then so it would always work. So our steps are, step 1, show it works when n is 1. Step 2, we're going to have to make an assumption that the formula works for any value. So we're going to say it works when n equals k. And then we'll show it works for n equals k plus 1. So we're just saying if it works and then it works for the next number, k could be 1, and so then it would work for the second one and then the third one and so on. If you're proving a sum formula, you'll want to use this, which is the sum of the terms through k plus 1 would equal the sum of the terms through k plus the k plus 1 term. So this is like adding the first 10 terms would equal adding the first 9 terms plus the 10th term would give you all 10 terms. So let's try this on our first example. All right, 5 plus 7 plus 9 plus 11 plus 13 plus blah, blah, blah equal plus 3 plus 2n equals n times n plus 4. All right, so let's break this down. The 5 plus 7 plus 9, those are all the terms. So that is the formula for the term an. And when I add it all together, we get this n times n plus 4. So that is the formula for Sn. All right, so now we're supposed to follow the steps. Step 1 is to show it works for n equals 1. All right, so the sum of 1 would equal, it's n, so it's 1, times n, which is 1, plus 4. So I just took my sum formula and I plugged in a 1. And that gives me 5. Look at that. It matches the sum of the first term. It matches the first term. Step 2. Assume our sum through k terms equals, all right, so now I'm just going to plug a k into the sum formula. So it'd be k times k plus 4. That was exciting. Step 3. Now we need to show that it works for k plus 1. Since it's a sum formula, our sum through the terms k plus 1 would equal the sum of the terms through k plus the next term, which is the k plus 1 term. So again, this is like adding the first 10 terms. It would be the same thing as adding the first 9 terms and then adding the 10th term. So substitute k plus 1 into the sum formula. So that'd be k plus 1 times k plus 1 plus 4. So this is the n and the n plus 4. Equals s of k, so that's k, k plus 4. So that's plugging k into the sum formula. Plus, and now I need a of k plus 1. So that is taking and plugging a k plus 1 into the a formula, which was 3 plus 2n. So it'll be 3 plus 2 k plus 1. Just take the k plus 1 and plug it into that formula. And then you just simplify both sides. On the right, so I combine the 1 and the 4. On this side we could distribute, so that'd be k squared and then 4k. And then we could distribute the 2 would be 2k and 2. On the left we could FOIL, so we'd have k squared, 5k, 1k and 5. Could collect like terms. I have 4k and 2k. Then I have 3 plus 2. So let's see. I'll have 2k plus 6. Sorry, k squared plus 6k plus 5 equals k squared plus 6k plus 5. Notice both sides are exactly the same. Thus it's equal. Since it's equal, that means that adding up all the terms through k plus 1 is the same as adding up all the terms through k plus the next term, which means our sum formula works. Let's try another one. So we're going to prove this formula. Again, the left side are all the terms. So n times n minus 1 would be the formula for an. And when they're all added up, we get the thing on the right, which is our sum formula. So that'd be Sn. Let's work through the steps. Step 1. Show that it works when n is 1. So I'm going to put a 1 for the n in the sum formula. If I do that, I'll have 1, 1 minus 1, 1 plus 1 over 3. So it'll be 1 times 0 times 2 over 3, which is 0. Now we check. Does that equal our first term? Well, that does equal our first term because 1 minus 1 is 0. Step 2. Assume that it works when s is k, or when n is k. So we're going to plug in a k for the n. That was real exciting. Plugged in a k for the n. Step 3. Since we're doing a sum, we're going to prove it works for k plus 1 by saying the sum through k plus 1 equals the sum through k plus the next term. So again, it's like adding up the first 10 terms would equal the same thing as adding up the first 9 terms plus adding in the 10th term. So I'm going to take my sum formula and I'm going to replace the n with a k plus 1. So it's n times n minus 1 times n plus 1 over 3. That equals s of k plus a of k plus 1. So I need to take the a formula here and put in a k plus 1. So it's n times n minus 1. Do some simplifying. This would be k plus 1 times k. All right, multiply things out. I'm going to multiply the binomials first, which would be k squared, 2k and 1k would make 3k and 2. Boy, I'm going to run out of space. Again, I'm going to multiply the binomials first. So that would be k squared. That is 1k. That's minus 1k. Cancels out. Minus 1. And then that would be k squared plus k. All right. I'm going to make these common denominators. I'm going to multiply by 3 to go up here where I have space. All right, distribute the k, so it'll be k cubed plus 3k squared plus 2k over 3. On the other side, distribute the k, all of k cubed minus k over 3 plus 3k squared over 3 plus 3, oh no, plus 3k over 3. Ran out of space, sorry. So it looks like I have k cubed, I have 3k squared, and I have 3k and a negative k, so that'd be 2k over 3. And hey, look at that, both sides are the same. Since both sides are the same, the formula works. All right, let's prove something slightly different. Let's prove that n plus 1 factorial is always greater than 2n, where n is greater than or equal to 2. So step 1, we're going to show it works when n is 1. Oh, wait, but n starts at 2. So we're actually going to try it when 2. All right, so if that's the case, we'll have 2 plus 1 factorial, and that should be greater than 2 to the 2. So let's see. It'd be 3 factorial is greater than 4. 3 factorial happens to be 3 times 2 times 1, which is 6. 6 is greater than 4. Works. Okay, we're going to assume it works when n is k. So we're going to replace the n with k. And we're going to have to remember that little bit there. And now we use the k plus 1. So if I plug in a k plus 1, boy, we have to figure some things out, don't we? Well, this would be k plus 2 factorial. We would like to get our step 2 assumption to show up in what we have. So let's work at the factorial. K plus 2 factorial would be k plus 2 times the next number smaller, k plus 1, times the next number smaller, k times k minus, oh wait, all that would be k minus 1 factorial. Because the factorial is that number times everything smaller. On the other side here, when we add exponents, it happens when we multiply with the same base. So this would be 2 to the k times 2 to the first. Notice that is the assumption. So that works because it works when we plug in the 1, and then the outer part, anything plus 2 is greater than 2. So since it's all true, it's all true. And our last example. Prove that 4 is a factor of 5 to the n minus 1. Well, step 1, let's show it works when n is 1. So 5 to the 1 minus 1 is 4. 4 is definitely a factor of 4. Step 2. We're going to assume the k works. So 5 to the k minus 1. We're going to assume that that has the factor of 4. And then step 3, we do the k plus 1 thing. So we'll have 5 to the k plus 1 minus 1. Well, we're going to add nothing but change the way it looks. What we're going to do is we really want this to show up. So I'm going to subtract 5 to the k and add 5 to the k. So if I add and subtract the same thing, I added nothing. Just changed the way it worked. Alright, so now I have the assumption. Now we just need to take the other part and show that 4 is a factor of that. So what could we do? Well, we could take the 5 to the k plus 1 and rewrite it as 5 to the k times 5 to the first. Then, if we group that, we could factor out 5 to the k, and it'd be times 5 minus 1. So in other words, that's 5 to the k times 4. Alright, so 4 is a factor of the first part since it's something times 4. I can divide the 4 out. And this is assumed to be 4 as a factor of it. Therefore, 4 must be a factor of the whole thing. That's it for today. Have a good day.